Do you know primary beams should be designed as unrestrained beams? In this tutorial, you will learn design of unrestrained beams through practical examples. This is part 14 of lecture series on steel design. For other parts, please have a look at description down below. Hey friends, if you're new here, I am Dr. Javed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examined life. In this tutorial, I will solve two examples. By the end of this tutorial, I am confident that you will learn design of steel unrestrained beams and you will be able to confidently carry out the calculations. These two examples are, first is unrestrained beam with a central point load, and the second is unrestrained beam with 3 equal point loads. And this is the one which is the non-standard one, and you will see how do we use the formula for C1. Let us solve first example. Before I start first example, I would like to cover basic design steps for unrestrained beams in this recipe slide. All you need is just this slide to be able to design unrestrained beams. And you know that the design process for unrestrained beam isn't much different to design of columns. Only there is a difference of one equation, MCR, a nasty one, which is a long one. But the good news is that you don't have to remember that equation. It is already given to you in my lecture handouts. The first thing you want to do is to classify the section. The next thing, you want to determine if buckling check is required or not. And for this, we have lambda dash LT is equal to under root WPLFY over MCR. And MCR can be found using this formula. If you cannot find it out using this formula, or if there's a chance of making mistake, then you can find out lambda dash LT using these three formula for different steel. But always remember that this will give you a very conservative solution. Lambda dash LT using MCR will give you the exact solution. Once we have determined lambda dash LT, then we have to see that if lambda dash LT is less than or more than 0.4. If it is less than 0.4, then reduction is going to be nearly equal to 1, which means that we will just be checking MCRD, or plastic resistance of the section. This also means that buckling is not happening in unrestrained beam, and MPL is equal to WPLFY over gamma M0. If it is not less than 0.4, the range is usually between 0.4 to 1.2, which is the intermediate range in which majority of off-the-shelf sections or practical sections lie. If lambda dash LT is greater than 0.4, then we have to check buckling resistance. So MED over MBRD, MED is applied, MBRD is buckling resistance, should be less than or equal to 1, where MBRD is equal to key LT WYFY over gamma M1. Key LT is a reduction factor, which you can find out using this formula, where phi LT is this one, and you get value of phi LT from table 6.5 and 6.3 in Eurocode. This is the entire process for design of unrestrained beam. If you simply understand this one slide, then 99% of the job is done. Now let's get to our first example. We have this point load applied here. Assume that the load is not destabilizing. Now destabilizing situation exists when secondary beam is resting on top of primary beam. That means that both beams can move against each other, although they will be connected. So this situation exists when the compression flange of a beam or tension flange of the cantilever, both load and the flange are free to deflect laterally. We have a beam, a primary beam, where we have a design load equal to 147. Load from secondary beam applied to the web of primary beam and restrained laterally at the end by simple connections. We say that LCR is equal to 0.85L, which means that there is a connection which is providing a little bit of a restraint. It means that it is a semi-rigid connection. So that's why we have taken 0.85L. For simple connections, we always take LCR is equal to 1 times L. And the length of the member is 5 meter. K is simply this factor, 0.85, which we multiplied here. So we have
LCR, which we will determine. So LCR will be equal to 0.85 times L. So first we will determine MED. If we have point load applied at the center, then MED is going to be PL over 4. If we have UDL, then M is equal to WL square over 8. So let us try this section 3, 5, 6, 171 and 51 UKB, and the steel grade is S275. We have to show that this is inadequate. So using the formula, MBRD is going to be reduction factor times section modulus. If it is class 1, 2 section, then it will be plastic section modulus. If it is 3 section, then it will be elastic. But for most of the sections which are available in section table, they are class 1 or 2 sections. MED is 184, which we determined in earlier slide, PL over 4. Okay, P is 147, L is 5 divided by 4. This is the formula from structure analysis. Here, loading is given to you, but in real life, loading will not be given to you. So you determine this loading yourself. So you have load transferred from slab to secondary beams, and from secondary beam, this point load is coming as a reaction from secondary beams. We multiplied with the factors to work out this load. This is not just there and then you just design it. So the way it works, so consider the load path. So from slab to secondary beams, from secondary beams to primary beams, and then from primary beams to columns. We have to determine NBRD. Here we have to determine its buckling resistance. But normally we would work out this lambda dash LT slenderness to see that if buckling check is required. So normal process is classify the section lambda dash LT to see if buckling check is required. If it is less than 0.4, then only check cross-sectional moment resistance, MCRD. If it is more than 0.4, then check buckling resistance. So once moment is checked, then you have to check shear resistance as well. But most of the time, shear is all right for unrestrained beams. And then you have to check serviceability or deflection as well. But deflection is most of the time for most practical beams, deflection is fine as well. So if you have checked buckling moment, it will almost certainly satisfy shear and serviceability. Here, shear and serviceability is not checked in this example. But in real life, you will, although you will check it, but it will not be a critical property. It will not be kind of dominant factor in terms of designing unrestrained beams. So now I have to determine NBRD. And the key thing here is to find out this key LT. I will go to section table and then I will find out these values. Only thing new here is this IT and IW. So a warping constant IW and torsional constant IT. So we will be using these. Key thing to note here is that this is decimeter power 6. So make sure you convert units in millimeter power 6. 1 decimeter is equal to, I think, 100 millimeter. This is in centimeter power 4. So make sure you convert it. The other parameters, I think you already know. So IZ is radius of gyration in Z. Capital IZ is second moment of area in minor axis direction, because this is going to deflect in minor axis, not major. So don't use IY. Load is applied in Y direction, major axis, but this is going to deflect laterally. So this will cause lateral deflection. So we will use second moment of area in Z direction, which is minor axis direction. And then IT is the torsional constant. IW is warping constant. So this is centimeter power 4, and you have to convert it into millimeter power 4 by multiplying it with 10 to the power 4. This is in decimeter power 6. So 1 decimeter is equal to 100, and then you simply put this power. It will be 10 raised to 12 millimeter power 6. WPL is plastic section modulus in Y direction. We will need it. And FY, because we're using S275 steel. E is Young's modulus, and E over G ratio is 2.6. So if you don't remember it, shear modulus for steel structures is normally 1/3 of the Young's modulus. But to be precise, E over G ratio is 2.6. We will need this over here. I mean, I can write it as, if I delete this G from here, I can write it E over G here, and then here I can simply plug in the value. Firstly, let's determine lambda dash LT, which is WYFY over MCR. I need MCR first. We have determined MPL. MPL, this comes from the section table. We multiply it with FY, and then we times it with 10 raised minus 6 to convert it into kilonewton meters. So we will need this MPL. Because this is the point load, if we go back to the table, we will know that for point load C1 is equal to 1.365. So now here you can see that if you have a point load, this is this situation where you have value of C1 equal to 1.365. If you had UDL, then simply you use value for UDL. LCR is equal to 0.85L, which is given here. Length is 5 meters, so multiplied, you will get 4250. Just plug in these values. Now, if I am carrying out these values separately with hand calculations, I normally divide it into 3 parts. And then in that way, chances are that I will not make a mistake. Otherwise, I mean, almost certainly I will make mistake because my calculation ability is probably not very strong. So I divide it into 3 parts when I'm working out hand calculations. So 1 and 2 and 3. And then I put it back into this equation. In that way, I will not make any mistake. Important thing here is that you need to have consistent units. If you do not convert units, then it will be trouble. And also, to see that the values make sense. If this is 246, this value could be 400 or something. It could be more than that. And it can't be like in millions. If it is in millions, it means that you have made mistake somewhere. Here, substituting value of C1 and then E for most steel members is 210 gigapascal. If I write it in Newton per millimeter square, then it will be 210,000 Newton per millimeter square. E, Young's modulus for steel is between 200 to 210 GPa. So take anything in between or maximum or minimum values. And then here you can see that I have converted this value of Iz into millimeter power 4. And IW, warping constant, it was in decimeter power 6. I've converted into millimeter power 6 in earlier slide. Make sure you convert it, otherwise you will make mistake. And Iz is second moment of area in minor axis direction, and LCR is again critical buckling length. IT is torsional constant, and this has been converted into millimeter power 4 as well. And then pi. Now, I have written this G over E as E over G in denominator, which I can do, because if this is being multiplied here, if I want to bring it here, if I cross this, I can write it as E over G. And value of E over G is 2.6. Then Iz, again, second moment of area. Now, this will give you everything in Newton into millimeter. So I will convert it back into kilonewton meter. And this will give me 328 kilonewton meter MCR. This is elastic critical moment, beyond which if you have a very large section, it will come back to its original position because deformations are elastic, as you saw in video earlier. Now, I need to determine, first of all, lambda dash LT. Lambda dash LT is 0.866. Now, see that this is in between 0.4 and 1.2. It means that this beam is in intermediate range. If you recall, this is 0.88. This is somewhere here. So it means that it is an intermediate range. If it was beyond 1.2, then it will be slender, and less than 0.4, then it will be stocky. Now, this is greater than 0.4. It means buckling check is required. Now, I need this phi LT formula. For this phi LT formula, I need alpha LT. So for alpha LT, for this section UKB 3561751, I will find out H over B first. So H over B is 2.07. 2.07 means that it falls into this range. The curve is going to be C. So for C, I have value of alpha as 0.49. This is where we got the value from table 6.2 and 6.3. For curve C, alpha LT is 0.49. So if you put it back here, you will get value of phi LT. Once you've got value of phi LT, then you can put it into this formula 1 over phi LT plus phi LT square minus 0.75. The only difference here between columns and beams is that we have 0.75 here. So if you put it back, you are getting key LT as 0.77. So when you are getting it as 0.77, you simply multiply it with the plastic modulus and Fy. This is from section table Fy because we used S275 steel. 10 raised minus 6 to convert it to kilonewton into meter. Our capacity is 178. Applied is 184. Certainly, I mean, it is greater than 1, so which means that this section is unacceptable. What do you do in this kind of situation? When it is really close, I would normally go for a higher section. So when you have demand versus capacity utilization ratio should be kept between 85% to 90%. We can actually modify this, and then if we use this modified procedure, which then it is taking it to very close and it's satisfied. But I want to show you one more thing. Now we did all this exercise, but we can do this in interactive blue book for this section. Here you have buckling moment resistance. It is directly given in interactive blue book, not in the section table. So if you click on that, our value of C1 is 1.365. Our length is in between 4.25. So that is in between these two values. So it will give me about 180 or so. So this will give you the value of NBRD directly. So whatever we did, it is actually already given to you in interactive blue book. So which means that why do we study all this? And the reason we study everything so that we have background, because otherwise if you say someone, okay, use C1 and C2, if somebody doesn't know how to use it, then the consequences could be catastrophic. Sometimes this may not be available. You might be checking some section which was 40 years old, which is not being produced in the UK. Then what do you do? Then you have to check it manually. These calculations are done for you as well in this interactive blue book. So you can directly find out MBRD from here. If you are practicing engineer, then you would simply find it from here.
Let us now go ahead and solve our second example with unrestrained beam having 3 equal point loads. This is the second example. In this example, unrestrained beam shown in this figure is simply supported between A and E, and the beam has a cross section of 914, 419, 388 UKB. Steel grade is S355. The section is really very heavy and the steel grade is high as well. The permanent action GK and QK, they are given. GK is 150, QK is 200 kilonewton. Obtain the elastic critical buckling moment MCR and prepare sufficient design calculations to check buckling resistance of the beam. Part B is how does cross-sectional shape influence the buckling behavior of the beam? Compare and contrast tubular and I-beam sections. Part B is a theoretical question, which is open-ended question. And as you know from theoretical background, that tubular sections are the most effective one in resisting lateral torsional buckling. And most of the time, they don't buckle at all. I-beam, on the other hand, buckles. But I-beam is one of the beam which is most effective in resisting vertical loading. So this is the beam that we want to design. It has got 3-point loads. W is the design load. So first we will work out the design loads. Let us see how we can solve this example. Now here, the first thing that I want to do is to work out the design load. You know that design load is equal to C gamma G GK plus gamma Q QK. When we put all these values, C is 0.925, gamma Q is 1.35, GK and QK, they are given. We get this W, which is our design load. It means that the value of W will be over here. And then we work out bending moment diagram. For bending moment diagram, we have a 3W total load. The reaction will be half-half, 1.5, 1.5. The bending moment diagram at the center will be equal to 1.5 times 6. 6 is the lever arm, which will give me 9. And take away moment generated due to this load. This will be W times 3, which will be 3W. So 9W minus 3W will give me 6W at the center. At 1/4 of the length, I will get 4.5W. If I multiply these W values, I will get actual diagram as this one. Applied bending moment will be the moment which is the maximum one, which is 2924. This is my applied moment. Now here you can see that this moment diagram is not the standard one. If I compare it with the standard diagrams, you can see I cannot see any diagram which matches with my requirements. I have this one, but certainly these are equal point loads and there are only 2-point loads. In our question, we had 3-point loads. This means that I have to use this formula for C1, where this psi factor is equal to minimum moment divided by maximum moment. Now, firstly, we have to work out MCRD as well to see that if the cross-sectional resistance is fine. From table 3.1, Fy comes out to be 355. I'm not going into details because I've already discussed it in design of tension members. Feel free to have a look at tension member design lecture, which is already on YouTube. MCRD is equal to MPLRD, which is equal to WPL Fy over gamma M naught. From here, I get MCRD as 6271. When I compare it with MED, you can see that MED over MCRD, it is less than or equal to 1, which means that the cross-sectional resistance is fine. Now here you can see that I haven't classified the section, but you have to classify the section. Section classification is our first step. As you know that this section is really very heavy. That's the reason I haven't classified the section, because almost certainly this section is going to be class 1. And I have used the formula for class 1 over here. But you have to classify the section. If you don't know how to classify the section, have a look at YouTube tutorial on section classification in the link down below. Then the next step is to work out lambda-LT, and I'm going to use the accurate method, which means WPL Fy over MCR. Now here the key thing is to work out this psi factor, which is minimum moment divided by maximum moment. If you have a look at this diagram, minimum moment is 2192 and maximum moment is 2984. So if I put these values, I'm getting psi factor as 0.75. Then simply I have to plug in this value of psi in this equation and I get C1 as 1.12. Once I have C1, then simply I can use this MCR formula. So I've obtained these values from section table. If I put all these values here, I will get value of MCR as 4685 kilonewton. From here, I will put it into this equation lambda-LT. It comes out to be 1.2. Is buckling check required or not? The answer is yes, because lambda-LT is equal to 1.2. As lambda-LT is more than 0.4, it means that buckling check is required. And I will be using this reduction factor approach to work out MBRD. Now here I will use first of all H over B. For the section, I obtained these values from section table. This is more than 2, so buckling curve C. This is from table 6.5 and table 6.3. If I put all these values in this phi LT equation, I will get phi LT as 1.24. Then I will put everything back into phi LT equation. And from here, I'm getting phi LT as 0.52. This is the reduction factor which I'm going to apply to the plastic moment. Phi LT WPL Fy over gamma. This is gamma M1. If you put all these values, you will get value as 3261. So MED over MBRD will be equal to 0.9. This means that this section is fine in bending. The second part is a theoretical part. It's open-ended, so tubular sections are very strong in lateral torsional buckling, but it's very difficult to pass services through tubular sections. Tubular sections are less efficient in resisting vertical loading as well as compared to I section. I sections are the most effective one in terms of economy and in terms of resisting vertical loading. Thank you so much, and I will see you in my next lecture. Keep watching, and if you have any questions, put below down in comments. I'll be able to respond to them. Thank you.